Alright, awesome. So our project explores various stopping criterion for data collection of a task called distributed NLI. And so first I'm going to talk a little bit about NLI, what that is, and then describe what distributed NLI extends from NLI. I'm going to then go on to sort of one of the stopping criterion that we've tried, and Phyllis is going to talk about how we're testing that stopping criterion in a realistic situation with real data. So natural language inference is a task where the input is usually two sequences of tokens. One we call a premise and one we call a hypothesis. So the premise, the idea in the task that we're really interested in is to predict whether or not the premise implies the hypothesis. So here the premise, one example, the boy was shivering, so he put on a jacket. And the hypothesis is that the boy was cold. So clearly here, this is entailment. So the premise implies the hypothesis. Some more examples. A woman is talking on the phone while standing next to a dog. The hypothesis here is that the woman is walking her dog. So if you start to think about this one, it's not so obvious actually, because depending on what you think walking means, either this could be a total contradiction because they say that she's standing, or you could interpret that walking is just that she's out on a walk with her dog, right? And then you say that this is neutral. There's no implication. And this is really common natural language. And an issue with NLI, because usually we just pick the majority label, but we don't want to throw away that information. Like we have this information that both of these labels seem sort of valid. And so what distributed NLI tries to do is just say, instead of picking one single truth, let's try to model the distribution of human opinion on that specific sample. So what does that look like? If we get one input pair here, what we would do in data collection is we ask a ton of people what they think that that input pair should be labeled with, and then we tally up their score. And the task that we're now interested in is to learn and predict what that tally is going to be. Like how many people are going to say what for this input pair. Importantly, this is a multinomial case, and actually for our project, we're going to simplify this into a binomial case where there's just entailment or not entailment. So one thing that is introduced when we do this is the cost of getting this data is super expensive. Because just for a single data point, we're going to have to ask a ton of people to label that give us some label. And so that's the main motivation of our project. Can we reduce the number of samples that we have to get and still sort of have a good estimation of what the real distribution of human opinion should be? And our intuition for doing that is maybe some of these input pairs are easier to label than others. So maybe some we could just have a few people annotate it, and that's a good estimate of the distribution, where others need more. And so the critical question to answer, if you're approaching it this way, we frame as how many samples, let's call that n, do we need to be confident in our estimate of p? Here, p is just going to be the portion of people that say that the input pair has entailment versus 1 minus p would be not entailment. So that's set up as a binomial, and the intuition that we use to derive n is that n will depend on p. That for different values of p, we might need different samples. So we use some confidence interval to derive this. And the details of that isn't important, but here they are. I'm going to skip to the next slide where we get our value of n as it depends on p. We can plot what that looks like if we know what the true p is. And what we notice is that as p is closer to 0 or 1 off to the sides here, we need less samples to be confident in our estimator of p than we do when it's closer to 0.5. And that lines up with our understanding of the binomial, because the binomial has a higher variance as you go closer to 0.5. Also in our derivation, you'll see that the variance of the binomial shows up. So based on our derived value of n, maybe we can define some stopping condition during training. And so how we would do this is we say, if we've collected k samples, we use those k samples to have some estimator of p, and since we don't know the true p, just use that estimator, plug it into our formula, we get n, and if we've already reached a number of samples for which we would be confident, that we would stop. So here are some experimental results on synthetic data for using this stopping criterion. And basically the takeaway from all of these experiments is that it's a pretty good baseline stopping condition. We beat some heuristic tactics and just static sampling. But for some more intelligent baselines, we're not beating that. And the intuition behind the issues we're having with our stopping condition is that we are doing poorly on predicting p's close to 0 and 1. And so that is sort of the next step that we want to fix. But another issue is that all of that was synthetic data, so what does it look like if we use real data? Phyllis is going to talk about it.
So what we want to do is to test these different stopping criteria, we're going to implement the distributed NLI model and use those results as our baseline. So we're going to train using two different types of training data set. So SNLI and NLI is what Rich had kind of presented before. And then also an alpha NLI, which is a slightly different version of it. And so we have to train these two separately. And so we're using the pre-trained Roberta large model and using the hyperparameters that they mentioned in the paper, except for the batch size, which we use a smaller number because of the memory limitations of the TPU. And these are kind of our results compared to the paper. We can see that for the most part, our numbers are a little bit worse than theirs, but they're pretty comparable, and we think this is mostly because of the smaller batch size. So our next step is to try other approaches at getting a stopping condition and extending the stopping condition to the multinomial case, improve some of the statistical properties mentioned today. And we're going to apply our stopping conditions to real NLI data sets to reallocate budget and gather more data sets.
Yeah.
So for the binomial and multinomial, you mean that, so in this case, you are treating as for a single data point, the derivation neutral that are independent of each other?
Yeah, well, so that's also true. Like, so basically what we're assuming here is that there's only two labels, entailment and non-entailment. And in natural language entailment, the task, people generally might frame this as entailment, neutral, and contradiction. And so our stopping condition doesn't apply to that because it's derived from the confidence interval of a binomial. And so we want to extend it to the multinomial case so that we can treat these three labels and do something for that.
Thank you.
Yeah.
So in your synthetic experiments, could you say a little bit more about what the baselines you were comparing to were doing?
Yeah. So some of the baselines here, these heuristics that we are beating, we are getting lower, just lower absolute errors, and we're collecting far fewer samples. The heuristics would be something like if the first 5 annotators agree, then you stop, and otherwise you collect a whole bunch of samples, like 100. And the other sample here is if the first 10 agree. And then the baseline that we can't beat is to just take the average number of samples that our adaptive scheme uses and just get that. And the reason is that we get really good predictions of P in this case when it's close to 0 or 1, because we're way oversampling what we need to. In our case, does poorly here. These two plots don't really show it, but so the y-axis here should be our estimator P, and the x-axis is the true value of P. So this is our adaptive sampling, and this is the baseline that we can't beat. It's a little bit tough to tell, but we actually are beating this baseline when it's close to 0.5. But we're not beating it on the ends, and so I think that this is an artifact from the confidence interval that we're using. Even though we tried to not use an interval that assume, or like we didn't use a normal approximation, so it's not because of that. But yeah, so we're gonna try other things. Cool.
Okay,
All right.
thanks a lot.
Thanks.